say win
Collectively?
1,000. Pardon?
Collectively?
No, each individual. So you spin this big wheel, and it will come up, and the numbers range from, because I'm terrible at writing and I'm lazy, I just put 5 to 30, just as the same example. And this is 5 to 30, but then this is the second spin. This is the first spin and the second spin, so you get 2 spins. And really what Joe is saying is, oh, this is kind of interesting because it's an interesting probability problem. And it is. So to get one of these, right, to just get one of them, it's a 1 in 7 chance. Well, if it were up to 30, okay, but it's up to 100. So it's 5 to 100, right? And you get 2 spins. So 5 to 100, if you did this truth table, you'd get roughly, you'd get different probabilities. But if this were, you had to score 30 points, and you got 2 spins, and there's, what do we count, 6 sides to the wheel, be a total of 42 events that could take place, of which only 6 of them are winners. And the 6 of them, the first spin you get a 25, the second spin you get a 5. So that counts to 30, right? So the 30 wins, right? So it's a combination of the two, it's an addition. And it's very similar to, if you guys are interested in going to Vegas and playing craps or something like that, that it's very similar to a truth table that you would use for dice, right? So you get one die, you get a second die, and you roll them, or you roll them together. It doesn't really matter. It's just that the combination of the two. Now, if you have one where you throw one and then you throw another, all you do is you put in the second column, or in this last column, like another throw, right? And then you calculate. So suppose what you're interested in is you want to be able to roll 7. Okay. So 1, 6 wins, 2 and 5 win, 3 and 4, 4 and 3, 5 and 2, and 6 and 1, right? And I just recognized that I screwed up the previous one. So what happens if you roll 1 on the first one? You can only get a 6, right? And with this one, you have to roll a second one anytime. So you can't do a none, okay? Because 7 wins, right? So this goes away because it's not possible. You get 36, and there's 6 of them, so it's 6 over 36, which equals 1/6, right? Okay, now suppose you got 3 people that are doing this independently, right? You got 3 contestants that are doing it. So what's the probability that all 3 of them credited?
One-sixth to the third power.
Yeah, so it's 1/6 times 1/6 times 1/6. Yeah, which is the same as, right? And you can see that it's vanishingly small to have 3 independent events that take place.
216.
Yeah, it's 1 out of 216. So
1 out of 8,000 for the odds.
for the Price is Right wheel? Yeah. So it's rare. It's rare, but all it takes is, I don't know how long that show's been in existence, but probably a long time, right? I remember it as a kid. So it's been around for a long time, and suppose it runs 5 days a week, something like that. So 5 days a week, that's 2,000 episodes a year. 2,000 episodes a year, assuming it doesn't do any other times like holiday times. So 2,000 episodes a year times, right? No, that's hours. 50 weeks. 50 weeks times 250 episodes a year. Yeah, it's 250 episodes a year. Over how many years do you have to get? 8,000 episodes. And the probability is now, you need 8,000 episodes to have a probability, an assurance, probabilistically, that there's going to be one. But is that true? Why not?
Well, I guess nothing is assured because each event is independent.
Yes. Yes. It's the gambler's fallacy. All it takes is one event, one episode, and the one episode is 1 in 8,000. These are independent events. Don't fall for the gambler's fallacy. I was setting you guys up. Where did the eraser go? Is there an eraser sitting around here? Shit. All right, hold on. I'll be back.
I can go grab napkins.
Can you grab an eraser?
You got paper towels and spray it right.
Yeah, okay, whatever. Something.
That's a used napkin.
Thanks, Spencer.
What is Did you take those apples yourself?
I promise I won't give them back. Okay, so today what I want to talk about is I want to talk about the second project. And I have the events a little bit out of order because I want to talk about proficiency first, and then I'm going to talk about Bayesian statistics, soup to nuts. I've been looking forward to this class all semester. Because this is a time in which you should now have a pretty good understanding of little bits and pieces, but I'm going to try to tie it together in a story. Okay. Before I do that, I want to talk about proficiency in analysis. How you can view yourself, where you think you ought to be, where you are. This is all self-evaluation. I think it's very important for graduate students to evaluate their own progress in learning. Okay? And I'm not going to ask questions. Mostly, I'm going to ask questions that are rhetorical, but I want you to consider them about yourself. So think about it. Basic analyses in R. Don't answer. Just think about it for yourself. Right now, can you read in data? Can you run a regression? Can you recode a variable? Like recode it, transform it, do all sorts of things. Can you generate a random distribution and plot that random distribution? Can you sample from a random distribution? So not just generate a random distribution, but can you sample from it? Can you randomly sample with replacement and know what that means? Randomly sample with replacement from your own data, randomly sample from it several hundred times. Can you do that? The reason why I'm asking these questions is now is a good time to start thinking about what do you know and what do you not know? Because the second project isn't really going to weigh heavily on your R skills because you have a team. Your team to work together to leverage each person's skill in the team, okay? So I don't want it to be, this is not a guilt trip. This is like a halftime pep talk. Because now is the time where you can start looking at what you know and what you don't know and say, okay, if I'm going to be a lifelong learner, you from this class, you really do need to have some basic R skills. Simply because without them, it's impossible to do much in Bayesian statistics. There's no point and click for Bayesian statistics right now. Who knows? Maybe in 10 or 15 years, there'll be this new like hyphen Bayes. Or IBM will finally decide that they want to do something with SPSS rather than just let it lay dormant. Or they're, I think, investing a lot of time in HTML tables. They're really important, as you all know. That's why the university spends 10 grand every time they come out with a 0.001 upgrade. It's for ridiculous shit. But suppose that they turn around, they give you a point and click interface. Well, the SPSS folks already know that SPSS is incapable of a lot of this stuff. So they have hooks to allow you to read and process R code. So you know that if you learn R, it's not a wasted effort. R will still be relevant. So right now is a good time to start evaluating what you know and what you don't know. And during the project, now this is my transition to point one, is during your work with your project team, if you feel like you're struggling with some of the aspects of data analysis, work with the person who is proficient in R and ask them questions. You'll be amazed at how the R people are. Like they will say, oh, you know, it's funny you asked that. I don't know why I did this. I copied code from so-and-so, and you'll soon realize that, you know, a lot of proficiency in data analysis is just copying code and rerunning it and then making mistakes and then trying to figure it out. Okay, so I want everybody to be a little bit more involved, if at all possible, especially in areas that you don't think you're very good at. Okay, just trying to push the boundaries a little bit. I don't expect everybody to be expert in everything. We have this weird academia where all academics have to be expert in statistics and content and fantastic writers and fantastic speakers and really organized and great project managers. Well, I fail on like 6 of those 4. So I don't expect everybody to be expert in all of those, but what I do expect is everybody to try to figure out where your limitations are and to try to push them. And that comes in the process of self-evaluation, okay, and also working with your team to try to figure out where you are deficient and boosting yourself up a little bit, okay? So that's my halftime talk. Go get them. Ready, break. Aziz's like, oh, great. Today is the day I get to tie all of this stuff in, but you don't get to be passive participants. You get to ask me questions like, I have no idea why we read this. And that is excellent. That's what I want to know. Today, I'm going to glue together all of these ideas. And the ideas, I thought about this summer, and I'm like, man, I can't wait for whatever the date is today, the 20th. I told you, keep track. So here's our timeline and the stuff that I had you read. You started out with probability. And this is like a learning progression. Okay, probability theory. Now, why is it that you need to understand probability theory? Really, you need to understand probability theory for a few things. One is you need to understand ratios. Okay? And a ratio, as we know, is part to part. Why do you need to understand ratios? Well, this is a curveball in not statistics, not math. It's a curveball for humans. We don't understand this stuff really well. It's really hard to process. Because oftentimes ratios get communicated in weird forms. Like decimals. And we suck at decimals. I'm an engineer formally. I remember I had a 2.4 grade point average. Okay, think about that. Next time you walk across a bridge. That bridge could have been designed and overseen as it was being built by a person like me with a 2.4. Which means that given the fact that at Notre Dame, the curve, I don't know if it was for you, but the curve for us was a B minus. Means I was average, slightly below average. 2.5 was the average. And because most of our exams required us to learn about 40% to be average, because the exams were so freaking hard. So I learned less than 40% of the material that I was tested on. Think about that as you're driving over the bridges. I hope they were all MIT graduates that were A+ students. Back to ratios. Ratios are expressed oftentimes in these numbers and these decimal numbers that are difficult for all of us to interpret. And in fact, don't think that the MIT people have it any better. They misinterpret this stuff just like scientists misinterpret p-values. But it's really important for us to go back and not make assumptions that you understand what ratios are. Okay? All right. Now, ratios are slightly different than percentages. Why? Because a ratio is a part to And the reason why it's so critical for you to understand the difference between these two is because oftentimes when we talk about Bayesian statistics, we're really talking about percentages. And this part here, what you soon learn, and you probably don't know the name of it, but it's okay. I don't expect you guys to know all of the inner workings of your car. I expect you that if you have a driver's license, that you know the rules of the road, which I know none of you. Who's seen you out there? You're terrible. I'm the only good driver. But
Self-serving bias.
What's that?
Self-serving bias.
Well, of course, and I'm on my bike. I expect you to know like simple things like that there's a key. And for some of you guys don't even have keys. I don't understand that. But you have a key, and the key starts the car, and it starts your car, and it doesn't start anybody else's car. You know, there's some kind of rudimentary things. And if you think about the very, very high level of understanding that you have of cars, like how many of you actually know about internal combustion engines? A few of you, right? But it's not expected. When was the last time you ever heard that the driver's test was, thou shalt tell me what the enthalpy is of your engine? Like, huh? What's that word? For some of you, it'd be like, spell enthalpy. But you don't need to know all of the details. What you need to know is you need to be able to chunk pieces together. Okay, so what is this piece and why do I have it circled? It's because it turns out that this piece is critical to everything that we do from this point forward. And this whole is called the law of total probability. And I'm going to put an asterisk here because this comes back later. We come back to this thing here because we need to, because we don't understand these things and we misinterpret these things, so we put them into these things. Right? I'm being very technical right now. This is too easy to misinterpret. Okay? So we end up with rules of thumb, and I'll talk about that later. So I'm going to put BF next to it, okay? Next to this. Okay? What does BF stand for?
Best friend.
Base factor.
I said best friend.
Best friend. I didn't know that.
It is.
It is.
Yeah.
What the hell is it? What is it? BFF?
BFF.
Yeah,
BFF. What the hell is BFF?
best friend forever.
You guys don't have that. We are your best friends.
That's terrifying.
This is where we began, but I'm going to put little hooks in here as well. So best friend, right? Your best friend is the base factor, and it turns out that it isn't. And this law of total probability is another thing that you need to understand Why? When do we use the law of total probability? Not just for this, but when do we use it later?
To get the probability of the data.
Yeah, to get the probability. Well, what happens think about when we sampled and we carved out little pieces and we said, we only want this stuff, right? What did we do?
PDF. PDF.
PDF? Yep. And exactly. So what we wanted is we wanted always that the probability density function, that the area underneath it would always be 1.0, right? So we always want that because we always want it to be whole, but in order for it to be interpretable as a whole, we want it to be 1, right? So what did we do? Think about that. Remember we had this kind of weird problem? I'm gonna give you shapes and you're gonna have like this like PTSD flashback of previous talks. Remember that? Coming back in? Okay. And I said, all of this stuff, we don't care about. We only care about this. And this was one color. And let's see, I don't know how the hell to do this. That was another color. And I have different colors. I don't know why the hell I'm doing this hatching stuff. So we have one color versus another color, and I said, okay, now separate this big blob and only focus on these two things. So we're only focused on these two, and I said, okay, now we've got to figure out this, but the area has to be this. What do we call that? What's that? Yeah, the sample space, but remember we have to change the sample space from this whole thing to only this and this. I heard something over there. Yes?
That's the word, is conditional.
Well, it is a conditional, right? And in the conditional probability, we want to make sure that that conditional probability is interpretable from the PDF, so that the PDF, the area under the curve is 1. So what do we do? What's it called? I don't fucking know is a perfectly good answer. Okay, in this class, this is part of learning. Is that you get kind of pushed up to the boundary and you go, wow, I forgot that.
We have probability space or something.
Yes, it's probability space, but it's what we're doing something to the probability space. What are we doing?
Normalizing it?
Normalizing it and standardizing it. We are re-standardizing or recentering so that the law of total probability comes back and it gives us a 1.0, right? Okay. Sometimes we call it recentering. Sometimes we call it standardizing. Standardizing back to this. Okay, so remember we started with step 1 here, probability theory. Now you didn't know that that's where you were going. You were just reading all of this stuff and falling asleep after the 3rd glass of wine and wondering, when is this book going to end? And it ended, right? None of you are worse for the wear. Everybody's feeling pretty good now. Now I'm dragging you back to where you thought you would never return to show you that you actually learned something critical that carries from this initial reading. And this initial reading, if you didn't do it, go back and read it because it'll be easier. This is the reason why when you think of the helix model of learning, you do have to go back sometimes to kind of like shore up the patches in your quilt that are missing. Okay, I always like that. I like that analogy of a quilt is like a knowledge structure. Knowledge structure is like a quilt, probably more like it. And that we all have quilts and as our knowledge structure and the quilt has missing patches. So the reason why I asked you about proficiency and analysis, because that's the curveball that will keep you from being able to test any of these things and to learn anything going forward. Because if you can't do it on your own, okay? And I don't mean to like turn everybody into a Bayesian diehard where you're a pain in the ass to all of your friends and family and colleagues and advisors, because then I have to hear about it, not from your family, but from your advisors, yes. But I want you to at least be able to compare the results from models to subjectivist models, Bayesian models. But in order to do that, you need the tools. So you started here, and we learned a few little things that will bleed off into others. From probability theory, we then gravitated to Bayes' theorem. Now, why did we start with Bayes' theorem? Because it's a class on Bayesian statistics. And this is the foundation of everything that we will talk about throughout the entire class. Now, Bayes' theorem, the way we discussed Bayes' theorem was originally like, these weird shapes, okay? And the weird shapes for Bayes' theorem, we started with point estimates. Just like when I first learned physics in high school, we started off with experiments where it was like, imagine this little car with these squeaky wheels that have been in this physics lab since 1950. We're on a frictionless plane in a vacuum. And we wheel it down. Anybody go to that same high school that I went to? And you'd wheel it down, but we didn't have, you guys had fancy shit. We had this paper tape that was tied to this little car. And the tape would be pulled through this hole puncher. Shane, did you have this too?
I did have that, yeah.
Yeah, you went to my high school. And the little the little boxcar would go down this frictionless plane in a vacuum. I didn't know New York City had vacuums, but besides these type, but our room was in a vacuum. And here, this car would go down, and you'd hear the punch, 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 punch. So the tape would go through this little hole puncher thing. And then we'd spend, probably at least 40 tries trying to figure out why the hell the tape was getting caught up. And it would get like 4,000 punches in just one little tiny area and then break the tape. So we pull all of this apart, and we finally measure this, and I can't even remember, it's been so long, my physics professor or teacher would say, well, you're not exactly in a vacuum, and it's not a frictionless plane. We're like, no shit, wow, that's a brilliant insight. We had to make do with basic principles so that we could learn more advanced principles. Bayes' theorem, I gotta remember my physics teacher's name. You have to start with basic principles where you simplify things. For the most part, unless we're Joe and we want to know about the probability of the price is right thing, right? Which is kind of a cool experiment. It's a cool thing to think about so that you're not fooled by randomness and you're not fooled by uncertainty principles. So point estimates are actually pretty good. And in fact, we ought to be using point estimates for a lot of things that we do. Like, whether you should buy insurance on Amazon for your $300 purchase and they're gonna charge you $7.99. No questions asked insurance. Don't buy it. You gotta calculate the expected value. What's the probability that your $300 thing is gonna break? Find the expected value, and the insurance costs more than the expected value. Yep. They're actuaries, folks. They calculate this shit. And they calculate it using Bayes' theorem. So we talked about point estimates, and we talked about point estimates with this stuff. Now, why is this important? Because, as I said, one, this is the foundation for all Bayesian statistics, and two, it's the frictionless plane. It's the thing that allows you to kind of sort stuff I also talked a little bit about tying in probability theory to priors, and then we slowly work toward likelihood ratios. Now you don't know that, but we did. I showed you that there's multiple ways to calculate Bayes' theorem, and I showed you that there's a likelihood method and then there's the probability method. There's two separate methods, and we worked through that problem. We worked through this problem. And I gave you links to check that out. Now, why is all of this important? Because you need to know about likelihood ratios, because you need to understand about likelihood ratios to fully appreciate the fact that Bayes' theorem is a weighting of the evidence with your expectations. Priors are your expectations. Now later, after covering a little bit of the point estimates and the pieces, we moved over to frequentists. Why? It's because in order to learn, we always have to scaffold up from the stuff we already know. This was probably a little bit of a refresher for some, maybe novel for others, and maybe mind-blowing for a few. Okay? All right, now, doesn't matter what group you fall into, doesn't matter. So once you get accustomed to this, you can move forward. This, probably one of those three groups, you'd fit in for this as well. This is old shit. It's old stuff that you've been exposed to repeatedly, and that it looks familiar. And we talked a bit about the p-value. Okay. Why do we talk about the p-value? Because it's important. It's an important concept because it relates to the probability of the data given the hypothesis, and that factors into the likelihood ratio. Okay. So the frequentist models include p-values that are part of the likelihood ratio, and that kind of ties everything together between frequentist models and Bayes' theorem. And now what's unique is this expectation thing. That the expectation, and we talked about equipoise, and I said that in frequentist models have built-in priors. You don't need to specify them a priori because they're specified for you. So there are bridges. Those are bridges from steps that you already know. You've already walked these steps. But I walked you back down to them and I said, you know, there's some stuff that you probably didn't pay attention to on your way walking up the ladder of the frequentist models. So let's go back and talk about probability theory in frequentist models of things that you already knew. And let's talk about probabilities and how they're associated. Okay. But you should have been a little bit concerned because we're only talking about Bayes' theorem here. And we're talking about point estimates. But when we think about frequentist models, oftentimes we're thinking of populations, right? We're talking about inferences. And so I always like to put it, you know, that statistics and inferences in statistics, what we're doing is we are trying to draw inferences about a population. So the population is like this giant cloud, right? And what we do is we take one sample, okay? And from that sample, what we're interested in is making inferences about this population. Now, population in frequentist models is really simple, okay? It's not a census. Population is a hypothetical entity, okay? It's hypothetical. It doesn't exist. Even if you think that 50 states is the population of interest, you are wrong. 50 states is the census for what makes up the United States, but when you make inferences, you're making inferences about the probability of any state, or all states that could possibly be part of the US, not constrained to the 50 that we have today, because it's hypothetical, okay? It is unobservable. Remember the distinction between that and that and that, okay? And in fact, that. We draw inferences about populations of interest, wider, bigger, more important things than just, say, the population of George Mason, right? Because even that is in flux. It would be very hard to quantify what actually is the population, the student body population of George Mason, because it's seemingly infinite. Not that you guys die and are born routinely, but you know, it's that people drop out, but there's also this hypothetical that there are students that are going to be and students that were. And it's all part of drawing inferences about this hypothetical entity. Okay, now, that's really what frequentist models are about. And frequentist models are also largely based on normal distribution theory. All of what you've known and learned in frequentist models are based upon normal distributions. It's not that they need be, it's just that 99%, and you know, 78% of all statistics are made up on the spot,
Including that one.
including that one. 99% of all that you will read and probably be held accountable for in social and behavioral sciences is adequately covered by normal distribution theory. So why expand your horizons, right? I mean, I'm not telling you to be slothful, but I'm telling you that it's actually a pretty good strategy, that it's great coverage for the stuff that you really need to know. So normal distribution suffices. Why is this a departure from this? Well, it's because point estimates are individual probabilities, but they are very akin, to the p-values, these point estimates of inference. They're akin in that you get a singular value, you get a singular value. They're different in that the point estimates that you get from Bayes' theorem have nothing to do with the population. They have to do with the changes in your uncertainty. The frequentist p-value has to do with the population because it's an inference about the population parameters, okay? So there's a subtle change, and it might seem like picayune and maybe not terribly deep, but it is deeper. Because Bayesians do not care about the hypothetical infinite population. They care about uncertainty. They care about uncertainty. So what we are doing in Bayesian statistics is we're not talking about some hypothetical. We are talking, and we're not talking about data, we're talking about singular hypothesis. Not one that was given to us, but one that we generate. And we are talking about our uncertainty. We start with uncertainty, our expectations, and we end with what should we expect in the future. Okay? It's forecasting. It's like of rain. Okay? Now people think that when you stand outside and it's raining, that the probability should be 1.0. No, it's a conditional probability, folks. It's not, it's when the barometric pressure is this way, and when there's a high pressure system in this location and a low pressure system in this location, and the dew point is this, and go on and on with all of these things, that under all of those conditions, the probability that it rains under those conditions is X. And yet I still hear people stepping outside and going, God damn it, the probability was only supposed to be 0.9, and it's raining. Yeah. Okay. They're conditional probabilities, and they're conditional probabilities of point estimates to a degree, but really, if you looked at the meteorological results, they are distributions. In most cases, they're normal. They're normalized, but they're normal distributions. Okay, because a lot of
You just said
meteorological.
something, I didn't hear what it was.
Pipe down. Quiet. Leave me alone. I should yell at it. Google's gotten smarter than me, although Google was a lot smarter than me to begin with. So do you see that we went from Bayes' theorem to something that you understood, but parts of the stuff that you understood you probably didn't understand, and you probably didn't care to understand it, but then I dragged you through it, and then I dragged you back, and I talked to you about the combination and the connections. Now, the big part here is that it's distribution and inference bound. And if we only deal with point estimates, there's no uncertainty about point estimates, and that is a problem. So then you read a little bit about which led you what the hell is that? Back to distributions. So, probability theory to Bayes' theorem to frequentist models, and then I said it's a frictionless plane. We don't do that stuff. We need uncertainty. We need to understand the uncertainty about any point estimate. So we talked about distributions. Remember this. In a normal distribution, what's the best guess? The mean. What's your uncertainty about your best guess?
Or standard deviation.
Standard deviation, right. Now, this pertains to the sample. This is a sample statistic. Why? Because we have these letters. If I change these letters to these letters, right? All of a sudden things change. Because these are no longer this, they're this. Okay? So it's an important distinction that we're making, is that in almost all Bayesian statistics, we are interested mostly in the y's, and occasionally we're interested in the thetas, provided the thetas are things that they're not directly observable, they can be estimated, and they can be estimated so that we can forecast in the future. Okay? Now, I'll give you lots of examples about that in a little bit. But as we move from frequentist models to distributions, the only way to produce these distributions is slide. I'm going to break up this MCMC thing into different pieces. And this turns out, this transition from this basic stuff to here is really the crux of Bayesian statistics. It's what makes Bayesian statistics really complicated. When we talked about distributions, I alluded and I gave you readings for something really simple. I gave you some readings in Bayesian Essentials in R that has a wonderful table, and it's really hard to find this stuff, believe it or not. I searched through book after book after book all summer, and this was the only book that had it. That's why I've cherished this one book. Not all of it, there's no perfect textbook, but this one table I would love to just reproduce for everybody. And that was table 2.1. That table, you should copy it, take a screenshot. I don't know what the hell you do with your computers these days, but do something where you can actually save this and always refer to it. Why? Because those are shortcuts. I told you that the greatest thing is having conjugate priors. Conjugate priors means that the evidence and your priors and your posteriors all share the same distribution among them. And because of that, there's an update function. And it's arithmetic. We like arithmetic. And even if it's complicated math, you can even throw it into your computer and it will calculate this stuff for you. But the most important thing about this is simplicity. Simplicity is that conjugate distributions are really key. Life easy. It's arithmetic.
How do you know if all three share the same distribution?
Good question. You don't. The only way you can really be confident is have several data collections so that you see that the distribution from large sample sizes yield very similar distributions in terms of your expectancy. And so what you look at is you look at what do I believe the probability is of this parameter being this value, let's say. And I believe that it's going to be like that, right? And I've seen from the evidence and also from previous studies that the posteriors look like that for the most part. So shape-wise, they share the same function form. Okay, not the same, it doesn't have to be necessarily the same shape. It just has to be in the same family, okay? Because we know that that's a normal distribution just as much as that's a normal distribution, right? And you can also have close approximates, okay? So like a T distribution, which would have flatter tails like that, looks pretty damn close to a normal distribution, and it is. It also turns out that logistic distributions and normal distributions are pretty similar, except there's a weighting factor that you can have. So a lot of it is based upon theory, but it can also be based upon data.
Making conjugate distributions sort of like the idea of transforming scales into z-scores so that you can compare them?
Yeah, kind of. I think that's a nice analogy. Is that what it's doing is it's you're getting data and you're having expectations that all follow the same shape, right? And because of that, there are easy rules to combine this stuff, okay? Because those easy rules exist, you're essentially doing away with the nastiness of how do you combine your expectation with your evidence, That's where it's really hard. So as long as you know that there's a distribution, a common distribution throughout this whole thing, the life is pretty easy. Okay? And it is kind of similar to standardizing, so you can add stuff together and not know and not knowingly violate something egregious, or egregiously violate something that's important, right? Like adding apples and oranges sounds bad, but both of them are fruit, right? Make a fruit cocktail.
What happens if they're not conjugate distributions and you treat them as if they were?
And you treat them as such. What happens is, it's much like in frequentist models when you make assumptions about normality, right? Normality of residuals. One of the key assumptions in making inferences about in null hypothesis significance testing, but inferences about confidence intervals, right? The confidence intervals are symmetrical and that they're an accurate portrayal of the data that we. When we have violations of that, we have inferential errors, but in Bayesian statistics, mostly we end up having descriptive errors. When we have assumptions about conjugate distributions, we run the analysis, but now we have new tools. Before, we wouldn't know. We wouldn't actually know. And if we made a bad guess based upon theory or based upon data, we would never catch it. Now we have the tools. And in fact, that's the next step is what happens if you have a guess that you don't have conjugates? And you say, well, okay, my expectations and my evidence differ. So what do I need to do? Prior to this MCMC, which I'm going to break down in 2 seconds, has been around for a long freaking time. Haven't had the muscle, the computer muscle. Like I'm sure that the Russians probably put millions of people to death over this. They just had them sit there and like churn out number after number, creating all of these things. But a lot of this came from the Russians. The mathematicians were brilliant until Stalin put it into knowledge. We can talk about that later. During break, I'll tell you about Lysenkoism. MCMC has a really long history. And the long history really comes from a simple assumption, and that simple assumption requires a lot of computing power. But now, like my watch and my phone have enough computing power to do this. A lot of it is it's resampling stuff that humans would go to sleep over. So what is it that this is? So this is Markov chain, but I'm going to talk about this second. This is Monte Carlo methods. Everybody know where Monte Carlo is? Yeah. Monte Carlo. Yeah, Europe. Okay, we at least have the continent covered, the non-continent continent.
Is it in Monaco?
Okay.
Near Monaco?
Well, you want to give them your European education?
Don't have much of a European education.
Yeah.
But, I think it's in a small country between Italy and France.
Yes. Yes.
They have great taxis. All the taxis are Jaguars.
It's
And,
Yeah, exactly. There's a shit ton of money. And what do they do there?
gamble.
They gamble. Monte Carlo methods came about from a very simple aim. Money. How do you figure out what to gamble on and when? And the way we do this now is through resampling. So we don't even call it Monte Carlo methods anymore. We now call it resampling because it's more accurate. It's much more in our colloquial vernacular now as well. But Monte Carlo methods are a process, a random process of both generating data and sampling data. Monte Carlo methods are generate data. From that, we sample data. Monte Carlo methods are just like the roulette wheel. The wheel spins, the marble drops, there's a number, the wheel spins, the marble drops, there's a number, you keep doing it, ad infinitum. You eventually get a distribution of numbers that it comes with. From that, you can also, so that's sampling from a known distribution, okay? Or a known process. We can generate data given a known process, but we can also sample from a known data set, data source, okay? So sampling data, we can sample data at random and with replacement. Now, why do I emphasize both of those? When you sample at random, we are sampling any observation. Any observation. So it has to be observed. Now, if it isn't observed, and it's a hypothetical, you have to create a distribution of those hypotheticals. That's why generating data is first. If you already have data, you don't need to generate data because you've got it. Once you have these Ys, whether they were directly observed or whether they were inferred from the existence of a population, you then sample the data at random and with replacement. Now, why with replacement? Because if you ever think about these normal distributions or any distribution, the distribution has a height at any one of the points on this, and there are different numbers of observations, right? Think of it as, this is oftentimes referred to as the density. So therefore, you can take the area under the curve and it's 1.0. But more often than not, we're accustomed to seeing this as frequency, right? So we think of the height of this as how many units have we observed, okay? Right? Frequency versus density. Density is important because if you take the area under the curve in density, it always equals 1. If you take the area under the curve of frequency histogram, the area is the total number of observations, right? Okay, so think of this in the frequency standpoint as this is the number of observations. Now, if we randomly select without replacement, we will essentially only replicate as n goes to infinity the observed distribution. And we don't want that. Why? Because it reifies our data. Reifies. It tells us that our data is real, when in fact we don't know if it's real. It is just a sample. So we don't want to give it more importance than it really deserves. It deserves probabilistic importance, stochastic importance, that it has their signal to our data. There's also noise. So the way to take into consideration the potential noise is we sample with replacement. So think of it as the, remember the urn? Jesus, I'll read more about urns. I will drink more. If you have an urn and you have white and red marbles, okay? You reach in and you grab a red marble. If it's without replacement, you chuck it over your shoulder. You don't allow that red marble to be resampled again. But if it's with replacement, you take that red marble and you stick it back in the urn. You mix it around and then you sample again. So all it is it's sticking back the observation back into the urn to be able to be selected again. Why does that help us? Because it helps us potentially exaggerate some of the observed values of X by oversampling them to get us some uncertainty about the distribution that we've observed. So sampling with replacement is very important because it will not just simply reify or recreate the same distribution that we've observed. Yeah.
Does that include sampling NAs in my original data set?
Yeah. I mean, unfortunately, that is one of the problems, and we can talk about that later, because missing data handling procedures are very, very similar to this, like multiple imputation, very similar to this. And then what you're doing is you've gone through this Monte Carlo process, and then we're going to talk about the Markov chain.
So does this have like a systematic effect on your data? So as you approach infinity, does it make it more kurtotic or less? Or
Well, as long as it's with replacement, it's going to overvalue the things that are more prevalent in your observed data.
so it just like reduces the impact of outliers, basically?
It's going to reduce the impact of outliers. It's also going to change the shape. If you collect some data, do a histogram, like do a nice, shape, and then sample with replacement n. What do I mean by n? The same sample size you had to begin with. So let's say, for instance, that you had 100 observations. Let's make it complete though, okay? Let's not include missing data. If you had 100 observations and you sampled with replacement 100 cases from that and drew the distribution, do that. And what you'll see is the distribution changes the shape, the size, the parameters, the mean, assuming, let's say for the sake of argument that it's a normal distribution. So the parameters that you would be looking at or making inferences about are the mean, like where does the central tendency lie, right? The dispersion, like how wide is that distribution? The kurtosis, right? How flat is it? And then the skewness, where's the tail of this? These are all basic things that you guys have mastered in basic statistics for frequentist models because it's normal distribution theory. But if you do that, sample that 1,000 times and create, every time you create a graph, have it create a different color, right? So do it in ggplot where you have, you go through the whole color spectrum and you can see. And what you'll see is through this process of random selection with replacement, that the shape of the distribution will change. Now, Sam, let me extend your question and go to the central limit theorem, right? Because that's kind of where you were going, whether you did it or not.
Good job, Sam.
All right.
Yeah, well done. So there's one thing is that if you had an infinite sample and you sampled from it an infinite number of observations, which of course there is no infinite number of observations, right? If you had 100,000 and you sampled at random with replacement 100,000, but I'm not going to attribute this to your intent, is that would those distributions look alike or would there be some way in which it would change? And the answer is no. However, if the distribution comes from a real normal distribution, whatever the hell that would, according to Omniscient Jones, it's a real normal distribution your data came from. If you sampled with replacement the same n, but you did it 10,000 times, okay? Think of the central limit theorem. The mean of means, as you approach an infinite number of samples, the mean of means will equal the population parameter mean, right? And that's essentially what this Monte Carlo method is trying to do, is it's trying by brute force to generate the distribution that underlies the data. Even though the data themselves in front of you may not reflect the distribution that you observe. We see that a lot, actually. We see when we got this weird distribution like that, looks like a tooth, that oftentimes there's just something weird about this, that there weren't enough observations or something. And that when you sample from that, if there's a true underlying normal distribution about this, you do this 10,000 times, and slowly you get kind of a normalized distribution. Or you get two normal distributions, right? Distributions that are really far apart. And we get that oftentimes when we have bimodal distributions that are underlying it. So MCMC is not, or sorry, the Monte Carlo side is not moving us to reality, it's helping us approximate the reality. Now, that Monte Carlo method is the resampling stuff, okay? That's the stuff we needed in order to make use of computers today and not have the 1,000 humans sitting there doing this stuff by hand, right? So computers have made it really, really easy. What we didn't need computers for was the first part of the MCMC, but the second part that I'm going to explain, which is Markov chains. What's a Markov chain? I always like it when I ask you questions like this. It's like, fuck, I hope nobody answers that. I feel really dumb. Don't feel dumb. It's not something that you should necessarily know. That's why we're having class. I'm your tour guide. And I'm providing you guidance to learn how to do these things. The Markov chain is a critical assumption in the process of understanding distributions, of understanding how to draw inferences by brute force, not by simple arithmetic. We needed a simplifying assumption in this Monte Carlo method. Because the Monte Carlo method resamples a bunch of times, and then you get a result, okay? But where the Markov chain comes in, restriction. It does not allow stuff to get too crazy. Because bounded, it would just keep going on in infinity and never stop. Markov chains are a very, very simple assumption. By the way, they're oftentimes wrong, but that's okay. They are limitations on what we're doing that allow us some traction on a very, very difficult problem. These problems are called over-parameterized problems. There's too many things. There are too many people who may have done it, and we don't have enough evidence, so we have to simplify. Markov chain. Remember I asked you during the forum, how many of you are good storytellers? How many people said no? Some of you said, no, I'm not very good at storytelling. And you know who you are. And some of you said, yeah, I'm a born storyteller. I entertain everybody. The important part of storytelling is actually that you have an implicit understanding of Markov chains, except that you violate them. Violate them in such a way that it makes it funny. Okay, how? When you're a good storyteller, you go from one event to the other to the other. And eventually, if you're really good at telling jokes, you bring it back here. But that's a violation of the Markov chain. What is the Markov chain? That events are only related to the preceding event. Only related to the preceding event. In other words, you have to be born before you can walk. And you have to walk before you can run. That is a clear Markov chain. That there is a restriction on any other pathway to arrive at a state or an event. Chains are restrictions on the inferences that we make. Now, why is this a simplifying assumption? Well, what we're trying to do is we're trying to decrease uncertainty about a distribution that we don't know. We went from point estimates to frequentists to normal distributions, and we said normal distributions. Now you need to understand distributions and why distributions, because in Bayesian analysis, if you know that they're the same distributions, it's arithmetic. And then I told you, it's a convenient fiction. There is no such thing as conjugate priors. That shit doesn't exist. You gotta learn something that helps you. What helps you? Brute force. What helps you in brute force is this thing called MCMC. This is a general umbrella of all different types of methods, which gives Sampler, Metropolis, Hastings. There's a bunch of them that fall under this umbrella. Numerical methods. Okay, there's lots of assumptions underneath them. The key ingredient to this whole thing is Monte Carlo. It's resampling, but there's a simplifying assumption that makes the resampling tractable. It means that eventually it arrives at something that we can work with. And that assumption is called the Markov chain. When you invoke an MCMC algorithm, there's this whole random process. Words that you probably never heard of, like seed, right? To you, a seed was something that you bit into the apple and it got stuck in your teeth, or that there are seeds spread all over your ground and they're growing trees, like in my backyard, tears that I don't want. Seeds are weird things, right? But they're not what you expected in MCMC. The seed is a starting point for the random number generator, okay? That's one. So seeds are a starting point. This is a random process. There's this weird thing that you will see every so often called convergence or convergence criterion. You'll also see it written as iterations. The number of iterations have exceeded, like, you see this danger, danger, danger. There's all sorts of warnings. Those warnings have to do with the iterative process of sampling via Monte Carlo. Restrictive process did not allow it to reach some finite end. Now, the finite end, think of it as like dating before you marry, okay? You can go out and you can date hundreds of people and you date them, and all of a sudden you come to the realization, right?
It's a shitty way of looking at it, but.
Well, no, but what it did is it reached your convergence criterion, right? That you like this person enough and you hated the other people sufficiently that you reached this point where the love-hate is at a good balance and you're like, good. All right, I'm excellent. Let's do this. This is the way a statistician would ever think of dating. I know, it's a little bizarre. Sampling and its convergence. Now, without a restriction from Markov chains, there would be no convergence. Why? When you date, the previous date that you had will color your view of the next date. The same person, but let's say you date this one person and they have qualities that you're like, I don't like those qualities. These will affect your willingness to date a next person that has similar qualities. If you like those qualities or you didn't like those qualities, if you didn't like those, you would rule it out, okay? That's the Markov chain. The Markov chain in action. You guys never knew that. you're Bayesians at heart, and then there's a Markov chain that's in action. The thing about it is that you all have shitty memories, and that you only remember the previous person you were dating. When you get to here, you don't remember date number 1. You only remember date number 2. Now, why is that? Well, we want some restriction, but we want some freedom, right? So having a short memory turns out to be a good thing for you, because you might have been in a lousy mood and you dated somebody and you thought they had a terrible personality and you said, I hate that type of person, I'm never gonna date that person again. And then you date somebody with the exact opposite and you go, whoa, was I wrong? And then you swing back to person number 1 and you say, I can actually handle that. So what happens is, it turns out that you guys have cars, right? So I'm gonna teach you a little bit about your car, the amount that I know. Have you ever had a car that didn't have functional shock absorbers? Right? Drive down the road, you hit a bump, and all of a sudden it's like, whoa. The car, what it does is it just kind of goes, and then at some point it's like, the amplitude is about 6 feet. It's doing bunny hops down the road. That is called an undampened oscillation. That is your car on drugs. Okay? Drugs are bad. This is an undampened oscillation. So this is one of the problems that shock absorbers treat. And instead of that profile, instead it's that profile that we wish to have with our car. We don't want to hit a bump and have the car like spiral out of control. You can't even control it after a while, right? I had one of those cars when I was a kid. So when you have shock absorbers, what it does is it dampens the oscillation, and eventually the car goes back to driving smoothly, right? And you know that because all of you have cars with shock absorbers that are functional. And it's only when they're not functional do you come to the realization that there's something seriously wrong with my car. Dampened oscillation is what we're trying to avoid in this resampling procedure. The resampling procedure could actually spiral out of control. The Markov chain is the shock absorber. It is the shock absorber that allows the sampling to eventually find a date that's worth marrying.
So how would it do that? Would it just set a minimum value and a maximum value and
Yes.
between that?
Yeah, so it depends on the procedure, okay? But yeah, it has I don't want to use all these terms, but because again, it's like I've now opened up the hood and now I have to talk to you about catalytic converters and shit like that. You're like,
But doesn't that reverse the effect of random sampling in the Monte Carlo?
yes and no. It keeps the random process in check. It keeps it from going bananas. Because you want it to go bananas a little bit, but you don't want it to go totally nuts, okay? This is like dating on steroids. You want to go, partially crazy, but not overly crazy, okay? You want it to eventually find a solution. The aim is to get married.
There's some
aim-
things that are off limits in dating, is what you're saying.
Yes, absolutely. And that's what the Markov chain allows you to do. But so Aziz, your question is, yeah, it depends on the underlying model. So like a Gibbs sampler has a different convergence criterion than Metropolis Hastings, okay? And so essentially what it is, those are the engines under the hood.
Okay.
One engine takes gas, the other one takes diesel. Good enough. Each one of them has a different convergence criterion, like what matters most. okay?
So can we just replace that with a different sampling method that's not random and
Yeah,
that way
yeah,
we don't need
Yeah.
we don't need to dampen the oscillations?
yeah, you could. You could definitely do that. The problem with non-random processes, and even pseudo-random processes, like the ones that our computer does, is oftentimes it's too tied to the data. So you collect some data or you generate some data, and essentially what you're doing, if it's not random enough, is that it generates the same answer over and over again. But the answer is driven by your own data, and we don't want that, right? We don't want that. And in fact, that's really an important aspect of this random process. Scripted random, but it's still a random process. Is we want you guys to go nuts a little bit, right? In the dating process, but not too nuts, okay? Because eventually the aim is to come up with a solution that's actually interpretable. Because you could, if it were undampened, you actually could come up with, if you only had Monte Carlo and no M's and not that this Markov chain thing here as a restrictor, it would go off the rails quickly. Sorry. And you could actually generate a posterior distribution that looks nothing like your prior or your evidence. It is possible.
So why don't you just collect more data and that way you don't have to.
Spoken like a frequentist. Because sometimes all you need is just a little bit of evidence to push you one way or the other. No, seriously. Why don't you? And that becomes the critical element in Bayesian statistics. Why not collect more data for evidence? Because data isn't always equal in terms of evidence. You ended up collecting more data, and the evidence base is that you really ought to be uncertain, right? And so what you end up doing is, suppose that the real underlying distribution is uniform, rectangular distribution, and the more data you collect, the more uniform it gets. That's not the way our brains work. Our brains work, the more data we collect, the sharper the point gets around this point of inference, right? But we're not accustomed to having a stopping rule like that. Like, let's see if we can get maximum randomness. Check. It generates maximum randomness to allow us to get a better estimate for the distribution. Let's take a 10-minute break. I know I'm blowing you guys away. You're like, holy shit, what was he talking about? Take a 10-minute break. 10:40, right? 10:40. Ready? Ready, break. I got all these football analogies, and I'm not even watching football analogies. I'll be a soccer fan, I think.
Good.
You should.
Yeah.
Yeah.
You're gonna do what?
Who are you gonna support?
I don't know. There's this really cool thing where you take a questionnaire and then it finds a team for you.
Oh.
The English Premier League. Now it asked me what I prefer but it really should ask me what I've experienced. Because if it gave me more of what I've experienced, I will never watch soccer again.
You should create a data set
Yeah.
with all the clubs, then run an MCMC on there.
You know what? I'd do it with you guys if you were interested.
Maybe you're gonna tell us about Stalin.
Oh yeah! All right, you guys want to know about Stalin? So Stalin, I'm a science buff. I love reading about science and all that. So Joseph Stalin became really he was always really paranoid, but he was super paranoid about the potential for scientists to undermine his social policy. And his social policy was the Soviet Union was going to be the most outstanding in everything that we do. But most importantly, we are going to tell the people that we will be self-sufficient. So he hired this guy, Viktor Lysenko, to oversee the science directorate of the new Soviet Republic. And Lysenko had no background in science. Like he was, I guess, an agronomist, but he was like a failed scientist, and he really had no expertise in anything. But he was a bureaucrat, and he kissed Stalin's ass for a long time. So I mean, Stalin said, "If I could trust anybody, I trust you." And he entrusted Viktor Lysenko to come up with new science policies and emphasis. So the big one was that the Soviet Union would be independent for growing their own food and feeding their entire population. This was a big emphasis because, any of you know, you take a look at the Soviet Union, it's massive. There's a lot of ground. But 90% of the Soviet Union is tundra. Ain't jack shit that grows in tundra other than tundra. So he said, we need to come up with a way in which we can grow our own food and we can make our, have our own livestock and all of that thrive in these environments that are not suitable for plants and animals. So Lysenko funded through state dollars a quote research program that was very loosely defined as a research program. And they went to these far off regions and they thought, oh, we're going to try this in Siberia or, right on the edges of the desert. And they tried everything. Nothing worked. So they went to Cuba and took a bunch of pictures of crops growing in Cuba and published in scientific journals how great their new farming techniques were going on the tundra with pictures of Cuba.
Wasn't it blatantly obvious? It's like there's no snow anywhere. Like sprinkle cocaine around.
And there's no Inuit standing there going, where did these come from? No, nobody questioned it because they were constrained to only Soviet publications. The scientific community read about this and said, whoa, Soviet research program is really cool because, they could actually eliminate world hunger or, famine. If they could find a way to plant all these crops in these areas that were largely unfarmable, that would be like a breakthrough of breakthroughs. So the scientific community started reviewing this stuff only to realize that it was all a hoax. There was nothing that was working, nothing. He claimed that he had cattle that could be sustained in these far off regions, like humans can't live there. And he'd show these big fat cows and pigs and goats and all of that, really happy. And what they were doing is they truck them in, they put them on this land, take photos, and then truck them out. Now that they were good at. And they knew how to travel over land of tundra really well. And they took all these photos and they had all of this as evidence for how good it was. And then when the scientific community really caught wind of this and said, we got to do this, this would be great, they realized that it was all bullshit. And they refused. Viktor Lysenko would go and give talks to scientific organizations about the brilliance that the Soviet Union had for understanding how to grow crops and raise cattle in areas that were largely uninhabitable. So that's where that's my story about Soviet science. Now it turns out that psychological science is pretty much the same. So anytime we have these external incentives to find solutions, most of those solutions are probably not solutions. They look good, they feel good, and we all pat each other on the back and we say, man, isn't this a cool discovery? Only to find out that
It was just
yeah, it was a blip.
slip in her
I know.
Patrick, I'm thinking about maybe
We'll
doing
take
a
this.
Bayesian
She's
topic comps or what have been
I'll
topics that
share with you,
students-
just email me, and I'll share with you my whole directory of Bayesian methods. Yeah.
So something like, just because I thought last class was very interesting, a topic like Bayesian versus frequentist. Is that
You could do that, yeah, you could do that. I think what I would do is I would extend it a little bit. Talk to Jay, because he did Bayesian. Yeah, talk to him.
Did Melissa?
I have Melissa Smith's list.
Melissa Smith, if you want her to talk, you know.
I could tell you what it was.
Yeah, I do, because I was on a committee, so.
All right, I'll shoot you an email.
Yeah, email me about that though, because I'll give you the whole set of readings. This Google Drive directory started out as just an idea of getting together a bunch of readings, and now it's like metastasized into this crazy ass 400 articles. But it's great because these articles are hard to find. They're really, really hard to find.
Are they organized or is it just a list?
By author.
It's only
By
for-
author, okay.
Author and year. So what I would do if I were you is I would take a look at
I was
things
like,
that
this is a trick
are
question.
recent and like maybe some, just a few that are more historically based. Keep it simple for comps. You guys have all the wrong ideas. You guys have this idea that thou shalt punish thyself.
Yeah.
You can only really master about 30 to 40 articles.
Okay. I mean,
Maybe.
that seems reasonable.
And Jim and I are of the same mind. It's like, it's ridiculous. You guys will have like 300 articles and I'll say, how about 10?
Yeah.
Are you S. Kelly?
Yeah.
Yeah, so I have,
Share-
this is Melissa
share
Spacey.
Shane's, share
Okay.
Shane's
Yeah.
list.
Just send me an email and I'll send you my cons list. So this is a Google spreadsheet.
When are you thinking about taking comps, James?
I really want to take them in the spring.
See, that's what
Like,
I want
to
to
get them like May.
Have you submitted
Man, you guys
a
rock.
first off,
Everyone's
I haven't
back.
submitted it, no, but I'm close.
like a full journal?
Yeah, I'm
Okay.
real close.
Yeah. Because like the key to me is I've been trying to get it together too and trying to take it in spring.
By the way, I
And it was like I talked about Carol, Carol's like, standard in the
Good.
department is you have to have submitted it.
Yeah.
A full journal
I'm
that
trying
is
to
submitted
pull as
first.
many of these things as possible.
Because
As I
like
read
James
this, I'm like,
Walker,
oh,
nope,
that's kind of
Kelly,
like shocking.
nope, like. So
But I like
we should
the
talk to
dating
that
one because then,
Yeah,
it's
yeah, so
all
they're
you
threatening to
guys.
like make me do it later.
Yeah, I know, everyone's like, whoa,
No, like,
Markov
that's not a
chain.
rule, right?
Yeah,
Like, I just wanna get it out of the way.
Markov chain,
So-
philosophy,
Okay.
dating.
And you're
Good idea.
I think
classwork. after
Yeah.
this semester. Heck, yeah.
Yeah, just wanna get it out of the way.
Okay, so here we are at MCMC. And the reason, again, why we went to this tool is because we don't have the frictionless plane. And because we don't have the frictionless plane, we need to use a tool to help us figure out how to combine priors, probability space, with the evidence, which is the likelihood, right? And so we need to combine this stuff in what is called a joint probability space. The way to figure out this joint probability space can either be done by theory, right? Because if they all share the same distribution, theoretically, it's then math. Or we can do it by brute force. Because nothing of what we're interested in really matches the theory. The theory is nice and it's elegant, and if you have any opportunity to use the theory, use it. Use it. This is the preferred method. Even though it's potentially flawed, it's the preferred method, and you can always check the preferred method to the potentially flawed method by looking to see if they disagree. Okay? What you can do is you can make simplifying assumptions, right, Shane? This is back to your question. How do you know if you got these? Well, you don't. But you can try this, you can get distribution, so you get prior distribution, but you also get a posterior distribution by adding the evidence in the update function to the prior distribution to generate the posterior distribution. This one, nice. This one, not so nice. But we have tools to help us. The tools that you have learned so far in R implement different MC algorithms. Okay, now I told you before, trying to answer these questions, like what is the point at which you decide to marry somebody? What is that convergence criterion, right? And that convergence criterion differs by algorithm. Now, I don't want to open up the hood any more than I have, mostly because it's not that you can't learn this, it's that you have a restricted amount of storage space right now, and I don't want to dump it full of stuff that it really doesn't matter. Okay, it really doesn't. It doesn't matter whether it's a Gibbs sampler or Metropolis Hastings. Both of them are algorithms. There are others. There's a Manhattan distance algorithm. There's all sorts of things. Those things under the hood matter far less than the logical progression that I see. Precisely why I didn't want people to use Krushke's book, because Krushke goes through all of these details, like in excruciating detail, to the point where you're like, do I really need that? Maybe I need to know that. Maybe I should know that. And then what you end up with is you end up with 1 million golf balls flying in the air, expecting to catch every single one of them. It's not possible. This is the stuff I want you to catch. Underneath this are all of these names. Good to understand what those names are, because in general, the Gibbs sampler is the most flexible procedure. Metropolis Hastings is easy computationally, but the Gibbs sampler is the most effective. Okay, it's the most generalizable. That's why you have things called JAGs, just another Gibbs sampler. That's what it stands for. Bugs. Bayesian algorithm using the Gibbs sampler, or Gibbs sampler. We don't have MH in anything, I don't know why, but underlying your R code, if you don't use STAM and you don't use bugs or JAGs or any of that stuff, but you use just standard protocol of R, so there'll be like some sort of R function that will do, a t-test. That may use one of many different types of MC algorithms. It's less important that you know them directly. And later on, when you start to learn a little bit more about this, you'll learn a little bit about why Gibbs sampler is a little bit more effective. It's a random walk. Both of these are, Metropolis Hastings and Gibbs sampler are both what are called random walk procedures. They are literally random walks through the data. And if you learn a little bit about that, if you want to learn a little bit about this, read the book called The Drunkard's Walk. I mean, if you're into that stuff. But it'll give you a little bit of an understanding about why these things are actually quite profound. Leads us back to distributions. Like, why is it that we start with distributions and we end with distributions? Because a lot of what we're talking about here, either this method, the theoretical basis, or the brute force method, all arrive at the same endpoint. It's a distribution. And the distribution will be of some significance in terms of making judgments about what you are interested in. And these distributions lead to multiple things. One, they lead to an appreciation of evidence strength of the evidence, the persuasiveness of the evidence, as well as subjective changes. Suppose I have an expectation that I will buy a certain type of car. And I go and I collect data, and at the end of my data collection, I have multiple things that I can draw from. I can draw from that experience of whether the evidence is sufficient to change my view, my subjective view. But I can also use the evidence in addition to my expectations, my subjective, whatever, preference for the car or whatever, and I can compare what I thought beforehand combined with the evidence and what I now know afterwards for my posterior probability. So this second thing is really the prior versus the posterior. And that actually is quite illuminating in many instances, because you conduct a study, based upon your study, you will either change your subjective state or not. And what that tells you is whether your evidence, now I know this sounds circular, and in many ways it is, because it's tied to Bayes' theorem, whether the evidence was sufficient to move you in a different direction, okay? We all are in states of uncertainty about pretty much everything. But what we do is we collect data, and sometimes we're pretty easy with changing what we believe, because we start here. These distributions at the end are all affected by this process, by this Bayesian process. What we're doing when we talk about evidence is we are talking about ratios. We are talking about the evidentiary basis for making decisions. Okay? So we have an appreciation, that's one, but two, we make decisions. We don't make a big deal about this in Bayesian statistics, but we make a big deal about it in frequentist models. Why? Because there are inferential errors that you all learn about. And those have to do with, right, it's not just type 1 versus type 2 errors, but there's now a whole vocabulary that's associated with those. Let me just tell you a few of those words, and all of a sudden you'll be like, oh, shit, right. Power. That's one, right? Measurement error. Sample size. All of these things affect the decisions that we make, and we know that. Effect size. Those decisions that we make to go or no go. Right? I mentioned this before. Thing I really like by Fisher is the p-value is nothing more than an invitation to do more work in that area. I love that quote. I think that that is very cool, because if we actually held to that, we wouldn't have debates. We'd be standing around saying, yeah, there was a good invitation to do more work in that area, and it was fruitless. And that way we wouldn't feel tied or guilty or, tied to that finding. We'd say, there was an invitation. It said, come here. And I did, and it was a bad idea. But I don't feel bad about it. So the decisions that we make in Bayesian statistics are way different in many ways than the decisions that we make in frequentist models, because the frequentist models lead us to decisions that have more to do with our data than they have to do with our hypotheses of interest. The decisions that we have in subjectivist models are decisions that we're basing our judgments on the things that we wish to test. Let me reiterate that. In a Bayesian model, you're testing the hypotheses that you wish to test. If you do not do that, then you are guilty of being held to the null hypothesis significance standard. If you constantly test the null hypothesis, which, by the way, is what I'm having you accept in all of these projects, because it is the hardest thing to do. If you only test the null hypothesis, then there's not a whole lot of benefit of Bayesian statistics over frequentist statistics. But if you are forced to find evidence for the null, you are doing something that a frequentist cannot do. So therefore, you're using the tool and making a decision that a frequentist is not allowed to do. Right? How many times have you ever heard, it's okay to accept the null? And if you say even once, that must have been during a drunken conversation. Thou shalt not accept the null, right? We hear that a lot. It's okay to reject. You're not allowed to accept it. In Bayesian statistics, there are all sorts of decisions that you can make. And the decisions can pertain to unobservable parameters or observable parameters. We have changes in subjectivity and decisions that we make. The hardest part, because Bayesian statistics don't have rules. There aren't any rules yet, but brace yourself, there will be rules. The more people start using Bayesian statistics, the more likely it is for us to see heuristics. Heuristics are bad, okay? Do not, I plead you, plead with you, to you, do not ever embrace a heuristic. Those who stand around and say, oh, so-and-so says 0.7 is a good cutoff for alpha. Those people sound smart, but they don't know jack shit. You know what they know? They know heuristics. Avoid heuristics because it provides people the illusion of knowledge. Heuristics are bad. Just like drugs. Actually, heuristics are worse than drugs. So I'm calling it. Heuristics are bad because they lead you to make decisions that are probably not justifiable. Plus, they may lead you to make decisions that you don't even believe. That's where Bayesian statistics differ from frequentist statistics. Bayesian statistics are about subjectivity. And that's part of the reason why Bayesian statistics are so difficult to convince people to use in science. Because ultimately we would say that my change in uncertainty was sufficient that I'm willing to be. If that's the case, we're allowing science to be consumed at the individual level for subjectivity. What we're doing is we're saying that the beliefs are more important than the actual veracity of the evidence. We're saying that implicitly. But that's not exactly the way the Bayesians would view this, is that over time, there will be a change in uncertainty. You know that for the most part, there's no scientist that would ever say that there's a problem with the Earth's temperature. All scientists worth their weight in spit would say the Earth's temperature is increasing. It's pretty evident. And it's increasing over time. What we don't know and what level of uncertainty we have surrounds whether humans caused it. Okay? We don't know that. It's uncertainty. Now, you call me what you will. I like the outdoors. I don't care whether there's a lot of evidence or a little bit of evidence. I'm going to have LED lights in my house. So that there's a certain level of evidentiary basis that pushes us to behave in a certain way. With frequentist models, it's binary. It's either acceptable or unacceptable. With Bayesian statistics, it's a subjective experience. I don't need a lot of evidence to know that I can do just a little bit and, I don't know, maybe a fruitless effort and call it an idiot tax. I'm willing to pay that. That I will bike more, walk more, fly less, I don't know, eat stuff that's close by. I don't impose that on you guys, but I am recognizing that the basis for human-caused global warming is not high. It's not high. We want it to be high so that we can force everybody to do something new, which probably would be a good idea. But it's not high. It's just a subjective probability that we care about. The objective is we may never have enough data. Think of every area that you have read or been interested in social and behavioral sciences. Think about it just for a second. Think about a theory that you believe is like partially true. You feel it's pretty good. Think about it just for a second. Will you ever have definitive evidence? Ever? In some instances, yeah, probably. But at some level, you collect data and you reach a decision about the veracity of that theory. And that's where the Bayesians differ from frequentists. The frequentists are making decisions based upon not the theory, but the data, compared to a probability, compared to a hypothesis that they're not even advocating for. And what they're doing is they're drawing decisions about the veracity of their theory from that p-value. Now, I'm not picking on them because I'm a frequentist as well. But what I'm saying is that there's an illogical connection to what we're trying to do and what we can do. And in Bayesian statistics, we produce these posterior distributions that aren't neat, they're not clean. And in fact, in many ways, if they're generated by this method, they oftentimes don't even look like distributions that we've ever seen before. So therefore, parameters aren't really clear. Because you could have a distribution that looks like that through MCMC. And in fact, in many instances, they do. They look like that because the random walk procedure generates these weird looking amalgams of data. So don't expect certainty to come from this process. Don't expect there to be a cut score or this is the right way to think about things. Don't expect those things, and you will have a better understanding of Bayesian statistics. No heuristics, no rules of thumb. There are great rules of thumb, but I'm going to teach you a few of them that are useful because they tie back to basic probability theory, and largely they're wrong. But you need to know, and you can just do a quick calculation on the back of a napkin or something like that to tell somebody at the pub that they're full of shit. Very important. These are important conversations to have. You can settle disputes, but now you have Siri, and now I have a phone that talks to me, even when I don't talk to him or her or whatever. But you need to know some of these heuristics so that you can make decisions, because ultimately that's what you're going to do. At some point, there's going to be enough evidence to change your subjective probability, your outlook, so that your posterior changes enough for you to act, right? Soon you'll all be using LED bulbs, maybe. And that'll be the evidence. That'll be sufficient evidence for you to change your behavior and to move. That's a decision. So that is Bayesian statistics, soup to nuts. We're going to talk a little bit more about this process. But next week, what's next week? Is that the get together? Yeah. So I'm going to come here early on and I'm going to sit with you guys and I'm going to field all sorts of questions. The first one I was out of town, but also I didn't want to push you guys in any one direction, but I would encourage you to come as a group with questions and ask me, okay? It's okay. Because if I tell you this way, you'll all do it this way. And I'm trying not to push you guys in different directions. The coolest thing I saw from all of the different presentations is you all did something different. That's what I want. There's many, many ways to approach these problems. But now in this one, there's actually fewer. There's more degrees of freedom. So I want you to go off and venture forth and try different things. Remember that the focus of the project really is defending the null. So you can choose whatever null you want, but it's defending the null, telling me where the evidence lies. Now you've got more tools at your disposal. You understand a little bit more of the, the full process and by which you have learned Bayesian statistics. But you've got these things, okay? But don't be too tied to them, right? But you have this, and you can explain it more.
Sorry about that.
No, it's okay. Yeah, damn you.
Distracting me with the critical moment.
Yeah, exactly. But you understand these things, and you also understand that there's a limit to how we can process things. So it's in your presentation, and the way you write this up, and the way you communicate it. Remember, the writer has a tough job because the writer is telling the speaker what to do. You got to write the story so that it's compelling. Okay? Remember that your audience is your grandparents. Okay? Only if they're alive.
Cutscene.
Otherwise, it's creepy.
Yeah. Oh, wait, there's some criteria here. Your grandparents, except they have to speak English, because I only speak English. Barely. It has to be at a language that communicates exactly what you did, but without all the details, right? Think of your family's worst storyteller. Don't let that be you. Okay? Ever. But especially not on the 3rd. Okay? All right, so next week I'll be here, and I'm going to entertain all sorts of questions. And I'll be here as long as you want me to be here. And if you don't want me to be here and you find that I'm a distraction, you can tell me to go away. And I will go away into my office, and I will still be there, and you can come by my office and ask me questions too. Sound good? Oh, and Jake will be here too. Yeah. All right, ready, Greg? Woohoo! A few more hours closer to flying.
Where are you going?
Great Falls.
Oh,
Yeah.
you too?
Yeah. My car's all packed and everything too.
I didn't pack it all.
Yeah.
I'm just gonna do mysteries and then drive home.
Yeah. I'm gonna start separately to get back to my parents' place.
Oh, you are? Oh, okay.
Climbing, but
Okay.
I've never had a car, 2 rigs in the car.
That's way
Nice. Yeah.
It's like, I never plugged it in.
I was actually thinking about starting it today. But I have an idea.
It's broken.
I have figures of 8.
I do figure it out.
We can wrap up.
Yeah. We can
I'm gonna bring my son.
No, but we can, look at that disposable. What are you doing?
Yeah, that's
Trying
fine.
to-
And if you go down, it's
I was just saying, I don't want to bring up my later
I was giving you just better be brought into play.
but I'll just bring.
Are we waiting around for something? I thought we were meeting. I don't know, I still haven't read the best paper. Yeah, I haven't opened it, but it's been a couple days, so I'll start it today. So,
Poison it or something. You see,
Yeah.
Only person.
Alright, I'll see you.
The research.
Yeah.
To do now.